Hi everyone, Dankman here. So this video is meant for Wednesday, April 29. However, even though I'm going to make a new video about some new topics for Wednesday, April 29, this first video is about the assignment that you received on Tuesday, April 28th, shown here, which is just a very short set of 5 systems of equations problems, and the instructions are to solve each system of equations by whatever method you prefer. So I'm actually going to do each of these 5 problems and talk through some of the logic of them, and that's what this video is all about. So the first thing we'll do is try and solve number 1. Since we're solving the system by whatever method we prefer, we have to figure out what method we might prefer for solving the system of equations given in problem number 1. To do that, I have to figure out what methods I have available to me. So the first way we looked at systems of equations was by using graphs. And if we have a graph, we can see what's going on and find the solution. But if working with graphs isn't something that's easily accessible to us, we learned this other method called substitution. And if substitution got too ugly, we learned a third method called elimination. Now the bottom line is that you can use whatever method you prefer. And the key to this handout and similar types of challenges we'll be working on is figuring out which one is the easiest for you to do in any situation. The graphing method is one of my favorites, so I would look at that first personally. Even though I can tell these two equations will graph lines, though, I can't tell what kind of lines. It's not in y equals mx plus b form, neither equation is, so I don't really know what either line would look like, what its slope would be, what its y-intercept would be. I don't know a lot about either line. So I think graphing would be more work than it's worth. That leaves me substitution and elimination. What's important to remember about substitution and elimination is these are both methods to basically turn our pair of equations into a one-variable equation that we can solve. Okay? So I'm going to check substitution first and see how accessible that is to me. The way substitution works is we try to rearrange or solve one of the equations for one or the other of the variables. So we isolate the x variable or the y variable, and then we take that variable, the expression we found for that variable, and we plug it back in or substitute it back in to the other equation to create a one-variable equation that we can then solve. Okay? So I have to solve one or the other equation for x or for y. So let me just pull this first equation down, this top equation, 3x minus 5y equals negative 19. I know that if I wanted to use substitution here, I'd have to solve this equation for x or solve this equation for y. I'm going to give it a shot just to show you what I see. So let's imagine trying to solve this equation right here for the variable x. To do that, my first move is probably going to be to add 5y to both sides. And then I'm going to have to divide both sides by 3. And as soon as I do that, I can see that this, okay, I'm going to have to divide 5y by 3, and I'm going to have to divide 19 by 3. I can see that this is going to involve a fraction, a set of fractions that are not the easiest things in the world to do, to work with. So I may not prefer that. Ultimately, the key to this is understanding that I had to divide everything by the coefficient 3, this number that's multiplying by x. So as I look through this equation, I can just ask myself, do I really want to be stuck dividing everything by 3? And if the answer is no, because 5 divided by 3 and negative 19 divided by 3 aren't fun, then I can say, forget substitution with x. I don't like that idea. Let's not do it. I can check on y now. Okay, if I wanted to solve this equation for y, I would have to divide everything in this equation by negative 5, because that's the coefficient that's multiplying by y. And I can see immediately that I'd have to do 3 over negative 5, negative 0.6, and negative 19 over negative 5, so positive 3.8 as a decimal, and I could convert those to decimals, and I'm pretty good at it, but why bother? Because maybe I don't want to do substitution. Now, if you really want to, you can check for substitution, and it always works in the kinds of problems we're doing, but I'm actually pretty interested in just saying, okay, maybe substitution is too much trouble for now. Let me try elimination, and I'll show you why. Here's what I like about elimination in this case. I'm picturing in my head just adding these two equations together or subtracting these two equations together. And I can see that if I added them together, the x's won't cancel and the y's won't cancel, so I can't eliminate one variable right away. But if I could just get this right here, this y term to say double and turn into 10y, for instance, I could get the y's to cancel, okay? Or if you could get the bottom equation to be cut in half and divide everything by 2, that's another option. But I'm going to focus on multiplying. And so I think I'm going to try elimination. And the reason I want to try elimination here is because I think, okay, look, if I multiply the entire equation by negative 2 on the left-hand side by negative 2 and on the right-hand side by negative 2, I know that I'm going to get this negative 5y to turn into positive 10y, and that's what I need to get my two equations when I add them together to get this y variable to cancel out, or to eliminate the y variable. So I'm going to take the left side, 3x minus 5y, multiply that by negative 2, and I'm going to take the right side, negative 19, and multiply that by negative 2. Distributive property, on the left side I got negative 2 times 3x minus negative 2 times 5y is equal to positive 38. So I get negative 6x minus a negative 10y is equal to 38, so negative 6y, negative 6x rather, plus 10y equals 38. And I knew that's where I was headed. I knew that if I multiplied through by a negative 2, I'd get negative 6x, positive 10y, and whatever negative 19 times negative 2 is. So that means I have a nice equation here. The left side is negative 6x plus 10y. The right side is positive 38. So if I take this equation, 2x minus 10y is equal to negative 6, and I add on the left side, I add negative 6x plus 10y, and the right side, I add 38, okay? Then really, even though they look different, I'm adding the same thing to the left side, or an equivalent thing to the left side as I'm adding to the right side, so I'm not messing with my solution, and when I do that, I'm going to get negative 2x plus negative 6x, positive 2x plus negative 6x, and that's going to give me negative 4x. And then I'm going to get negative 10y plus positive 10y. That means I'm going to eliminate my y variables. When I add them, they'll make a zero pair and be eliminated. And then negative 6 plus 38 gives me positive 32. Dividing both sides by negative 4, I get x is equal to negative 8. And so I chose elimination this time because I saw that very nice opportunity to simply double the top equation and then cancel out or eliminate one variable easily. And once I have x is equal to negative 8, it's easy enough for me to take either equation. I'll just go ahead and choose the top one. Substitute negative 8 in for x and use that then to solve for y. Negative 5y is equal to, what is that, 5. Dividing both sides by negative 5, I get y is equal to negative 1. And so the solution that comes out is x equals negative 8, y equals negative 5, okay? And you can go over those last steps on your own. The point here being that which method are you going to choose? Graphing here seems hard. Substitution seemed hard using the top equation, but maybe I could have tried the bottom equation. But I just saw this quick opportunity to multiply by 2 and create easy elimination for me. So that's number 1. Next, we're going to look at number 2. So let's look at number 2. What method would I prefer for solving number 2? Well, the 3 methods that we've been considering are looking at a graph, using substitution, or using elimination. I love graphs. It's easy for me to see what's going on with a graph, and thinking graphically is often a nice shortcut. So I'm going to think about graphs first. As it happens, both of these equations are in slope-intercept form, y equals mx plus b, so it's easy for me right away to identify the slope and the y-intercept of both lines. I can see that the slope of the top line is negative 7 over 4, and the y-intercept of the top line is positive 4. And the bottom line, I can see the slope is negative 7 over 4, and the y-intercept is 2. So immediately I can see both lines have the same slope, and both lines have different y-intercepts. And this is the first thing we thought about when we did systems of equations. What do two lines look like? What kinds of options are there? So they have different y-intercepts. Okay, the top line has a y-intercept at 4, and the bottom line has a y-intercept of 2. Okay, they have different y-intercepts, but they both have the same negative slope here, which is negative 7 over 4. So they're both going to have the same exact steepness. So even though they start in different places on the y-axis, the top one starts at 4 and the bottom one starts at 2, they move the same way. They have the same slant or steepness, which means they'll never intersect each other anywhere. So I don't have to use substitution or elimination to know right away that these two lines will never share a point, which means there will be no xy pair on both lines at the same time, no solution, and I don't have to do any sort of equation manipulation at all. For me, that's the best way to solve this problem. As a side note, today's topic is what no solution looks like when you're forced to use substitution or elimination method, and I'll get to that in a next video. Let's move on to number 3. Number 3, the two equations are y equals x minus 2 and y equals 2x minus 2. I could graph these and find out where they intersect, and as a matter of fact, I recognize that they both have a y-intercept of negative 2. So just thinking about that really quickly, I know both lines are going through that point, 0, negative 2, no matter what. And I also recognize that one of them has a slope of 1, and the other one has a slope of 2. So I know they have different slopes. One of them is a little flatter, slope of 1. Oh goodness. And the other one is a little steeper, a slope of 2. So I can pretty much guarantee you that this is the solution to these two equations. And if you would like to see that demonstrated, I could take the top y and set it equal to the bottom y. So basically x equals 2, or x minus 2 should be set equal to 2x minus 2. And when I do that, this is a single variable equation that I can solve for x. So basically I could try this sort of substitution that we originally looked at in order to confirm the solution that I just found with the graph. However, to keep this video from running into the 20-minute range, I'm not personally going to do that. I'm not going to solve this equation, substitute back, etc. I'm just going to note, hey, I think the solution is 0, negative 2, because these two lines have that same y-intercept, and they have different slopes, so this is the only point that'll be on both lines. And if you want to make sure, you can plug the solution into both and check that it solves both equations. Next, let's look at number 4. Number 4, two equations. One of them is already solved for y. So for me, the easiest way to proceed is probably to take what y is equal to and use substitution. So I'm going to take negative 2x minus 3y is equal to 20, and I'm going to take the y variable in that equation, and I'm going to substitute and replace that y variable with negative 4x minus 20. And I can do that without messing with my solution because I know that y equals negative 4x minus 20 for this system. So now I've created a one variable equation with only x's, and I can solve that. The first thing I have to do is clean up the left side, so I'm going to have to use the distributive property here to do negative 3 times negative 4x minus 3 times negative 20 is equal to 20. Negative 2x plus 12x plus 60 is equal to 20. 10x plus 60 is equal to 20. Subtracting 60 from both sides. 10x is equal to negative 40. Dividing both sides by 10. X is equal to negative 4. I've solved for one variable. Remember, a solution to a system of equations is going to be an x and a y value together in an ordered pair. That means I need to also figure out what y equals. Conveniently, I have this equation already set up for me. Y equals negative 4x minus 20. So to me, it seems pretty straightforward to substitute in the solution I found for x and then to solve, or really just evaluate now, to figure out y. Y also equals -4. So in the end here, my solution for the system of equations is -4, -4. So this one seems like it's ripe for substitution. For me, that would be the easiest way to solve this system of equations. Finally, we'll look at number 5. Number 5. What method is easiest for us to solve number 5? Again, you can pick any method you want. Our 3 options that we really know anything about are graphing, using the substitution method, or trying to solve by so-called elimination. In this case, I'm not sure what the graphs look like. I don't know anything about the slopes and the y-intercepts, so I don't think graphing is going to be super easy. I could probably really easily solve for y here, or even x here, but to me, I'm really excited for elimination. And the reason why is I can tell that if I just add the top equation and the bottom equation together, I'm going to get these y's to eliminate very easily. So I'm going to take the top equation, I'm going to draw my golden road, and I'm going to look at the bottom equation. I'm going to say, look, the left half of the bottom equation is equal to the right half of the bottom equation. So if I add the left half and the right half, I'm not messing up my solution, but I can clearly see that I'll be adding negative y and positive y, which is a 0 pair. So that will make one of my variables eliminate. So I get negative 10x plus negative x. My y's eliminate, and I get negative 30 plus negative 14. That's negative 11x on the left and negative 44 on the right. So x is equal to 4. Now I need to pick one or the other of my equations. I'm going to use this one. Negative x plus y is equal to negative 14. And using the solution I already got for x, which is 4, I can now plug in 4 for x, and that gives me an equation with y in it, and I can solve that equation for y equals negative 10. My solution is 4, negative 10. The bottom line is, as you look at a system of equations, picking the method that's easiest for you is a cool skill. Number 1, I chose elimination for myself, but you could have probably done substitution. Number 2 seemed really a lot easier to do a graph or think about the graph. Number 3, it seemed easier to think about a graph. Number 4, substitution presented itself as the obvious choice. And number 5, elimination seemed easy for me, but you also could have done substitution. So that's review of different approaches that we've learned to solving systems of equations. And today's topic is actually going to be a new video in which I describe what it looks like to find no solution to a system of equations when you do substitution or elimination. And that looks a lot like the way no solution looked when we did single variable equations. So look for that video next.